Assalamualaikum warahmatullahi wabarakatuh. Today we're going to start covering the processes in the bulk deformation process. Basically, there are four main processes in the bulk deformation. We're going to cover two processes, which are rolling process and also forging process in this week. So let us look into the processes. So as I've mentioned in the previous slide, okay, so there are four basic bulk deformation process. There are rolling, forging, extrusion, and also wire and bar drawing. So as for the rolling, the slab or place will be squeezed between the opposing roll in order to decrease the thickness of the work material. And then second one is forging, which is work is squeezed and shaped between two opposing dies. Okay, and the third one will be work is squeezed through a die opening, therefore it will take the shape of the opening. And the last one, wire and bar drawing, will be the reduction of the diameter of the wire or bar by pulling it through the die opening. Now let us look into the rolling process first. Okay, so the rolling process can be defined as the deformation process where you reduce the work thickness by the compressing forces exerted through two opposing rolls. For example, like in the picture below. So this one is the schematic diagram for the rolling process. If you can see, there are metal here, okay, and then it going through two roller, and then the thickness of the part will be reduced. So the rolls perform two functions during the process. One is it will pull the work into the gap between them through the friction, and then the second one, it will simultaneously squeeze the work in order to reduce the cross section. Now, type of rolling can be classified into two. One is based on the workpiece geometry, and second one based on the work temperature. In workpiece geometry type, there are two, which is flat rolling. This one is basically to reduce the thickness of the rectangular cross-section bar, and another one is shape rolling, where the square cross-section is formed into certain shape like I-beam, U-beam, or railway shape, bar shape. Okay, so for the work temperature, it is produced via hot rolling or cold rolling. Let us look into some of the product from the that produced through the rolling process. So for example, the starting material here is bloom. Okay, so it is square in shape, and once it's done, it will become a structural I-beam like this one, or it can also be produced into the railway rails. Okay, the second one is slab. Okay, so this rectangular slab can be reduced in terms of the thickness, and it will become a plate or sheet or coil like this one. And for this one, it is a billet, so it can be reduced into a certain bar and rod after the finishing process. So here is the diagram of the flat rolling. So this one is the roller. Okay, so for this roller, there will be roll radius. Okay, and then in here also you will see the contact length, which is L, where the roller and the work material is in contact. Okay, so for the rolls, there will be a roller speed, which is VR, and in the same time you will see the work material here with T naught is the initial thickness and TF is the final thickness, and there will be V naught, which is the initial velocity of the work material, and VF, which is the final velocity of the work part. Now let us look into some equation that we have to know in this rolling process. Okay, so the first one is draft, which is the amount of thickness reduction. So this one is represent as D. Okay, so D for draft equal to T naught minus TF, okay, which is the T naught is the initial thickness and TF is the final thickness. So that's when you will get the thickness reduction. And then reduction will be the draft expressed as the fraction of starting stock thickness, meaning that it will become R equal to D over T naught. If we put the equation here, it will become T naught minus TF over T naught. Then you will get the reduction ratio. So here are some facts that you have to know about the flat rolling. So the area where the plastic deformation of the work material happen is called the roll zone. Okay, so this area, the material will deform into the shape that we want. And then what we have to know is when the metal enter into the roll zone, the velocity of the starting material is slower compared to the velocity after it entered the roll zone. Okay, so this roll itself will move at constant speed. So based on this judgment, it is said that there will be one point in the process where the velocity v naught and v final will be the same. So at this area, uh, at this point when the velocity is the same, it is called no slip point. Okay, so for before this point, the roll will be moving faster than the material. After this point, the material itself will be moving faster than the roll. So here we look it into the diagram here for better understanding. If you can see here, so when the work material going inside here, the initial velocity will be lower compared to the one that coming up from here. So of course, because the work material is very thick, so in order for it to enter into the deformation zone, it will become slower. But as for this one, the thickness is already reduced, so it will move faster. Okay, so it is assumed that there will be one point in here in the L area where there will be no slip point, where the same velocity of the rolls, the velocity of the work material and the roll will be the same. Okay, and so that there will be no slip on this one. Okay, so here is the one that we have to know about the no slip point in metal rolling. Using the same concept and assumption, so the equation is given like because it is assumed that at this no slip point, the velocity will be the same. So it is calculated, they come up with the equation where T naught, W naught, L naught will be equal to T final, W final, and L final. Okay, so if L value is changed in term of the velocity, you are going to get the equation T naught, W naught, V naught equal to T final, V final, and velocity final. So this one will be used, it's easier for us to determine the whether the thickness or the width final or the velocity final using this equation. Other than that, no slip point, or we call as the neutral point. Okay, so where the amount of slip between the roll and the work, this one we can measure using the forward slip. So the equation for the forward slip is given by S equal to V final minus V of the roller over the VR. So then you will get the forward slip equation. Based on this one also, we will be able to calculate the true strain. So the true strain, if you can remember from the previous example that I've mentioned, so the epsilon equal to ln T naught over the T final. So then you will be able to calculate the value for the true strain. Okay, so as for the average flow stress, you can still use the same equation, which is YF equal to K epsilon N over 1 plus N, and the draft also, the draft is the maximum thickness of draft can be done in one pass. Okay, so in here we can calculate it by using D max equal to a coefficient of friction squared and 10 times the roller radius. Okay, so it very dependent on the coefficient of friction and also the roll radius. So apart from that, the force that's supposed to be applied for the rolling on the roller also can be derived. Okay, so based on this one, F is force can be calculated by using average flow stress time the W and time the L. Okay, so we are going to see the value for the L, how the L is calculated. So as we already seen in the diagram before, L is the contact length. So the contact length is calculated by R in bracket T naught minus TF and then square root. So you will get the value for the L. And then we also can calculate the torque by using the T equal to 0.5 FL. F is the force, L is the length of the contact length. And then we can also calculate the power, okay, in order for us to perform the rolling process. So this one is calculated by using P equal to 2 pi NFL. Okay, 2 pi N, N is the rotational speed, F is the force, rolling force, and L is the contact length. Then you'll get the value for the power. So if we want to see the graph for the pressure in between the contact length, okay, so if you can see here, the pressure will start to increase until no slip point, that one where the peak of the pressure, and then it will start to decrease once it goes the no slip point. So this one all happen in the contact length area. The next point is shape rolling. Okay, so shape rolling is a work is deformed into certain contour cross section rather than the flat or rectangular shape only. So this one is accomplished by passing the work through roll that have reverse of the desired shape. So meaning that the roller is shaped into the inverse of the shape that you want to create. Okay, so the product usually created using this shape rolling are like I-beam, L-beam, U-channel, rail for railway track, and also round and square bar rods that I've shown in the previous slide. So here is the rolling mill for the hot flat rolling process. If you can see, the setup for the rolling process is very big and very hot. If you can compare the machine to the operator, which is just like a small person over here with a very gigantic process machine to perform the process. So due to that, the equipment is massive and very expensive. So in here, we are going to look into the rolling mills. So rolling mill configuration, there are 5 types of it. They have 2 high, which is only 2 opposing rolls, 3 high, where the work pass through rolls in both direction, meaning that they are stacking of 3 roller, and then we have 4 high where backing rolls support the smaller rolls, and cluster mill, multiple backing rolls on smaller rolls, and also tandem rolling mills where there will be sequence of 2 high mills. So here are the rolling mill configuration. Okay, so the figure here is, this one is for the 2 high, this one is too high. It's actually the work material going through here, and then it will go down here and on the configure the roller that is stacked together, 3 in like this one. We're going to see a video on this one so that you can see how the process take place. And then we have 4 high. So as 4 high, we have 2 big roller which support the 2 small roller here. Now here we see the cluster mill. You can see that there are 4 big roller which will support the small roller over here, and we also have tandem rolling mill. This one is for a continuous process, where if you can see, there are the stack of 2 roller here. Okay, the roller, but it is continuous, meaning that the material will go from one, and then go directly. So if you can see here, the thickness in between here will start to reduce from this one to another roller. Okay. The next thing that we are going to look into is the rolling type based on the work temperature. As we go on the introduction previously, I've already introduced to you three types of the working, which are cold working, warm working, and also hot working. In the rolling process, the working process that involved will be cold working and hot working only. So now let us look into the effect of the cold working on tensile strength, hardness, ductility, and the grain size. So what happened is when the cold rolling processes involved, the metal will pass through the roller at the temperature below its recrystallization temperature. So this one will increase the yield strength of the workpiece and also the hardness of the metal. Okay, so during this process, the strength and also hardness will start to increase. This is done by introducing the defect into the crystal structure in the metal, creating the hardened microstructure which prevent further slip. So if you can see, the original structure will be like this one. It is more rounded, what we call grain inside here. So when we perform the cold rolling process, the microstructure inside here will be more packed and smaller. Okay, so this one, what we can it can reduce also the grain size of the metal, and it create the hell patch hardening process, okay, inside the metal. So during this process also, the ductility of the material will start to reduce, okay, because of the changes that happen inside the microstructure. Now, let us look into the effect of the hot rolling. So, in the hot rolling process, the work material will be heated above the recrystallization temperature. So, for example, if the rough product with the last grain that being heated go through the hot rolling process, what will happen is it will deform the elongated grain into elongated grain like this one. Okay, so since the work material is still in the high temperature, so what happened is the new grain will start to form, and when the recrystallization temperature is reduced, okay, meaning the recrystallization complete, the grain will be a small and uniform grain. During this process, it will what we call it, we will improve the strength and also the ductility of the metal. During the rolling process, there might be a defect, okay, in terms of the processes. Okay, there are two common defects in the rolling process. The first one is crowning, and the second one is the thermal chamber that created into barrel shape. Okay, so let us look into the crowning. So if you look into the crowning, it is a bending of the straight cylindrical roll caused by the roll force produce roller strip that are thicker that at the center. So if you can look here, so the roller here, it become bent like this one, therefore it become a strip that is thicker in the center. Okay, so in order to overcome this process, this condition, we can do the grinding of the roll with the chamber to produce a strip with uniform thickness. Okay, so we can grind the rolls here so that it become what we call it become more uniform for the strip. Okay, so the radius for the chamber point is generally around 0.25 greater than the edge of the roll. Okay, so that what we call this area will become flat, the strip, it can become flatter. Okay, the second one is the thermal chamber where the roll are barrel shape. So this one is caused by the heat generated during the plastic deformation process. It makes the what we call the roller become like this one, like a barrel shape. So this one can be controlled by varying the location of the coolant on the roller for during the hot rolling process. So meaning that we can add fluid for to cool down the roller so that the roller shape will not become barrel shape. Okay, There are four types of defect in rolling product. So we look into the first one, which is called the wavy edges. So this is resulting by the roll bending. So when the roller is bended, it will create this wavy inside the workpiece. Okay, so the strip will become thinner along the edges than the center. Okay, and then the edges will elongate along its edges, and the edges also will strain from the expanding freely. So if you can see here, so it will create the waviness on the strip. The next one will be crack. There are two types of crack. One is zipper crack and another one is edge crack. So for the zipper crack, it results in the poor material ductility because the material is not ductile enough. So when we do the rolling process, what happens is it will create like a hole in the middle part of the sheet. Okay, so apart from that, it is also due to the center that is too thin. Okay, so for the next one is the edge crack. This one is resulting of the poor material ductility also, and also due to the rolling temperature. Okay, so for example, most probably the material is not ductile enough for the rolling process, so we have to change the process where we have to increase the temperature or perform it at a hot rolling process. Okay, so other than that, it might be because of the edges is too thin compared to the center. Okay, the next defect is alligatoring. So alligatoring is like this one. If you can see here, the work material or the what we call the strip is split into two and become like this one. Okay, so like the alligator's mouth. Okay, so this is due to the non-uniform deformation during the rolling process. For example, the force that we apply on the sheet is not uniform throughout the rolling process, so it can create this defect. And another one is due to the presence of defect in the original cast billet. Now let us look into other deformation process that related to the rolling. There are three other processes that we can look into. There are thread rolling, ring rolling, and also the roll placing. Now let us look into the thread rolling. So the thread rolling will be a bulk deformation process where we form the thread on the cylindrical part by using the rolling between the two dies. Okay, so it is an important process where usually it is used in the mass production of bolt and screw. So it is performed as cold working in thread rolling machine, and it gives some advantage to the thread over the machining process. For example, it can create higher production rate because it's faster compared to the machining process. It can also create better material utilization because there is no chip produced during this process, and it can give also stronger thread and better fatigue resistance compared to the thread cutting using the machining process. Here is the process of the thread rolling. So if you can see here, this is the thread, what we call the die that to produce the thread. Okay, so when we put the starting blank inside here, and it will move the die on this one, and then it will create the thread on the what we call on the starting blank here. Okay, so in the end, you will get this product. Let us look into the grain flow inside the what we call inside the thread that gone through the machining and also the roll thread. Okay, so in the machine part, when we perform the machining, we cut through the grain. Okay, so this one will what we call weaken the work material. So compared to the roll thread, what happened is the grain is a flow is deformed like this one, so make it stronger for the metal. You can look into the video for the thread rolling inside this link. Okay. Next is the ring rolling. So the ring rolling is a process where we want to create what we call a thick wall ring with smaller diameter, and then we roll it into a thinner wall ring but larger in the diameter. So a thick wall ring is compressed. It will deform the metal and make it elongates. then it causes the diameter to enlarge. So hot working process for large ring and cold working process is used for smaller ring. Okay, so usually the product will be like a ball and roller bearing cases, steel tire for railroad wheel, and ring for pipes, pressure vessel, and rotating machinery. Now let us look into the process of the ring rolling. So at first, the ring rolling will start with the ring of the metal itself, okay, and then when it goes into this process, there will be a reduction of the thickness by using these two roller, idler roller and also the main roller, okay, and edging roller will reduce the thickness on this area, okay. So meaning that there are two process happen at one time. Okay, at first the thickness on this area, and then the thickness from this area also will reduce at the same time. Okay, when this process happen, the diameter of the ring will start to increase. Okay, so this is how the ring rolling take place. So you can refer to the video using the links that I've put inside here for better understanding of the ring rolling process. The last process is roll piercing. So in the roll piercing process, where we want to create the hole inside the tubular part like this one. Okay, so what happened is the work material will be compressed from the top, okay, using this roller, and it will expand on the other side. Okay, so it will create the tensile stress on the side. Okay, so but then when it start to roll here, using this roller, it will maintain the diameter of the workpiece. Okay, so while the mandrel is going to pierce into the material, and then it will create the hole inside here, but then the diameter will maintain the same, only that the work material will start to elongate. Okay, so this is the roll piercing process. Let us look into some problem. Okay, so a 30 mm thick plate made of low carbon steel is to be reduced to 25 mm in one pass. Okay, so it's already given the D is equal to 25 mm in one pass. Okay, so in a rolling operation, as the thickness is reduced, the plate widened by 4%. Yield strength of the steel equal to 175 MPa and tensile strength equal to 290 MPa. The entrance speed of the plate is 77 meter per minute, roll radius 300 mm, rotational speed 45 revolution per minute. What they want is determine the minimum required coefficient of friction that would make this rolling operation possible, and B is exit velocity of the plate, and C is forward slip. Okay, now let us see some how this question can be solved. Now, it's already stated that for A, they want how much is the coefficient of friction, okay, the maximum coefficient of friction. So the only equation that we can use to calculate the coefficient of friction will be D max equal to coefficient of friction itself square times the R, right? So it's already given the D value, which is 30 minus 25, which is 5 mm. Right, so this one will be reduced in one draft, okay, one rolling process. So based on this one, we can calculate the coefficient of friction. Okay, so then the final value will be 0.129. Okay, the B question is they want it's given that the plate widened by 4%. However, it is not given the width of the work material, right? So so for this one, they want the final velocity, right? So the equation that we can use is the T naught W naught V naught equal to T final W final V final. Okay, so as for this one, since the plate is widened by 4%, meaning that we can assume that WF will become 1.04, meaning that 100 plus the 4% then you'll get 1.04 with initial. So when we put this value inside the equation here, you will get the since W naught you can take out, and then you will get the VF. Okay, so when you put it together, you will get the value 88.85 meter per minute. And then the last one, they want you to calculate the forward slip, right? So this one you have to calculate the VR first, which is 2 pi rn. Then you will get the speed, the velocity is 84.82 meter per minute. And then when you put it inside the equation here, which is VF minus VR over VR, you will get the forward slip is 0.0475. So the next question is a series of cold rolling operations are to be used to reduce the thickness of metal plate from 50 to 20 mm in reversing to high mill. So roll diameter equal to 600 mm, coefficient of friction of the roll equal to 0.15. Specification is that the draft is to be equal on each pass. So first, you determine the minimum number of passes required, and B will be draft for each pass. So when we are given this question, when minimum number of passes, how many times that we want to perform the draft to perform the rolling process, first you have to calculate what will be the maximum draft that you can achieve in one pass. Okay, so in here, so you can use the equation d max equal to coefficient of friction squared times the roller diameter. So based on this one, when you put the coefficient of friction is 0.15 times the radius for this one, for the roller. Okay, so meaning 300, so it will become 6.75 mm. Okay, so it says that minimum number of passes. Here we have to see how much is the reduction that we want to make, which is 50 minus 20, right? So meaning that we have to reduce to 30 mm. So you have to give T naught minus the T final, 50 minus 20 over the maximum, how many draft that you can create here. So it will become 4.44, of course, because the specification is given here is it has to be equal on each pass. Okay, then you can round it into 5 passes, but the meaning that the draft you can lower it from the 6.75. Okay, so then it will be 5 passes. So then what is a draft for each pass will be it will be then 50 minus 20 divided by 5, so it will become 6 mm. So here are some videos link, so you can look into the videos for better understanding of the rolling process. So that's the end for the rolling process. Thank you very much. Assalamualaikum.